Hello, my name is Klaus-Rudolf Kladny, and today I would like to present to you our work on causal effect estimation from two different data sets with continuous treatments. Specifically, we consider a confounded linear model where x and y are observed, while z is always unobserved. We assume access to one data set for each of the two structural causal models displayed here, where the left model corresponds to a setting where x is intervened on, while in the right model this is not the case and hence corresponds to the observational setting. Our goal is to estimate the parameter alpha, which characterizes the causal effect of x on y. While the data from the interventional setting is unbiased with respect to alpha, we see that this is not the case for the observational setting, where there exists a bias due to confounding. In practice, however, obtaining observational data is often much more feasible, which is why this data has the potential of reducing some variance. In our work, we consider a class of estimators that we call matrix-weighted linear estimators, where we weigh the least squares solution for both datasets via a matrix W. We're generally interested in minimizing the mean squared error with respect to alpha, and the theoretically optimal weight matrix for doing so is given as follows. Here, delta refers to the bias in the observational setting. However, in general, we don't know this bias, and also we don't know these covariances matrices. Hence, we consider a plug-in approach for these components as shown here. We see that well-known methods, such as data pooling and ridge regression, can be seen as special cases within our framework. For data pooling, we simply consider the least squares solution on the pooled data set, where xi is the interventional data and xo is the observational data. Then we see that we can rewrite the solution to the weight matrix as given here. Also, there exists a link to ridge regression, which can simply be recovered from data pooling by replacing the observational data by a scaled identity matrix and replacing the observational estimator by 0. This relation is displayed in the figure to the right. Finally, we see that our approach can outperform baselines such as data pooling and scalar weighting schemes from prior work, such as this Rosenman weighting shown here, especially in settings where the confounding is strong or the ratio of amount of observational data to amount of interventional data is small. Thank you very much.